Fixed points can be a little bit disinteresting at first sight. Essentially, a fixed point is just something that stays the same after a process is applied to it. More formally, a fixed point x of a function f satisfies the property that f of x is equal to x. Alone, theorems about fixed points and in fixed point theory can feel very unmotivated. But fixed point theorems are actually very important to the fields of topology, chaotic dynamics, and differential equations. The other really cool thing about fixed point theorems is there's usually a lot of generality in their statements. And so when you take those theorems and apply them to relatively simple scenarios, it can sometimes feel that they are producing impossible results. That being said, going a different direction with this, fixed points are also closely related to periodic points. For us, a periodic point p of period m of a function f has the property that f to the m of p is equal to p. Notice that this is a different notion of period than is used in the context of trigonometric functions, like sine and cosine. In those cases, the period or the periodic nature of those functions is referencing recurrence within the function. However, in our context, we're going to be thinking about recurrence after applying a function so many times. In other words, when we say a point P has period M, what we're actually saying is that the point P is fixed by the function f to the m, or f applied m times. To make this more interesting and to make sure that we're focused on non-trivial cases as often as possible, we will focus on points of least or prime period m, which are defined such that the first k greater than or equal to 1 for which f to the k of p is m. That was a mouthful in English, but hopefully the math I've written on the board is a bit more straightforward than the English it corresponds to. In light of the relationship between fixed points and periodic points, one of the more accessible theorems that uses fixed point theory in its proof is a proof about periodic points. It is a case of Sarkovsky's theorem, or more specifically, Sarkovsky's theorem when n is equal to 3, which tells us about the existence of periodic points for a given function. So if you'd like to start developing the ideas behind Sarkovsky's theorem in the case of n is equal to 3, you can go ahead and click on this video here. Otherwise, if you want to see some fixed point magic that arises out of an application of one of the theorems from fixed point theory, you can go ahead and check out some of those examples over here.